Welcome to IronBittle, a show where we look at the TargetBittle database and try to understand how it works, and crucially, not only how it works, but why it is coded the way it is. Because honestly, although TargetBittle might seem quite unusual in some of its design decisions like static memory allocation and desire to handle storage faults, actually, if you think from first principles, you sort of just realize that there's no our way to code database like this. Okay, so where we are at in our exciting IronBittle series, we started looking at the state sink. So as a reminder, TargetBittle is a replicated state machine. There is a cluster of 6 replicas, and these replicas maintain a so-called distributed log, which means that each of the replicas knows a sequence of prepares, and those sequences match across replicas. And the overall evolution of the state is that replicas append prepares to their write-ahead log. Of course, the problem here is that everything is finite, and in particular, the state to store the log is also finite. We cannot grow this chain of prepares infinitely. At some point, we should say, okay, we are actually cutting this chain. We are forgetting whatever happened in the past, and we are acting only on the current state. But that means that you need to have some way to transfer the state between the replicas. If a replica was not part of a cluster for a long time, and then it rejoins, it might be far behind in terms of log. So other replicas need to be able to transfer the state to the replica. And what we covered last time is that transferring the state is actually not as hard as it seems. So let's jump to the code and look at the superblock. So as a reminder, the root of all state in TargetBittle is the superblock. It is a small region of the data file which is, for redundancy, duplicated several times at the start of the data file. And in the superblock, we have the so-called checkpoint state. And the checkpoint state is the root of all state. So checkpoint state stores pointers to the manifest, And the manifest stores pointers to all of the tables of the LSM forest. So and the LSM tables store the data itself. In other words, if you have this checkpoint state, you could transitively reach everything else you have in your data file. And because we have physical determinism across the replicas, because we guarantee that all the replicas not only store the same data logically, but that they actually have identical data on disk. This checkpoint state, so only the pointers, is the only thing we need to make state sync work. Because in our grid, assume that you've synced checkpoint state. And now after syncing checkpoint state, you probably want to get your manifest. So you're going to go to the grid and use this manifest newest checksum manifest. You're going to use this manifest newest. Well, no, it should also have. Okay, yeah, this it is. You're going to use manifest newest checksum and manifest newest address to read the manifest block from disk. So you're going to go to the grid, and then you're going to call read block function, and you're going to pass this callback from local or global storage, meaning that you are fine with the block being either from your local disk or from any other replica in the cluster, which means that actually, you don't have to write dedicated code to say that, okay, after we have checkpoint state, now we need to fetch the manifest and then the preset and whatever. No, you just run your processor normally, and when it tries to read the manifest, it will ask the grid for the block, and then the grid realizes that it doesn't have this block, so it's going to ask the replica for the block, and the replica is going to ask one of the peers in the cluster. So that means that our state sync task is reducible to just syncing the checkpoint state. And okay, how do we do this? This is done as a part of start view protocol. So we are going to look inside this on start view function, which receives a start view message. And the start view message stores the atomic state of the VSR. Start view contains the current checkpoint, so this checkpoint state thing we've seen over here, and it contains the suffix of the log. So actually, let's just see how this start view is generated by the primary. I think there is create start view message. Okay, yeah. So if primary, for whatever reason, needs to create a start view, and whatever reason is either the primary started a new view, so it wants to say, hey, I'm now your new primary, or a Lightning replica asks the primary to create a start view. What we do, we update our view headers, which means that we essentially fill in the suffix of our log. And then in our message, we copy first the checkpoint and then the headers. So that is the start view. And that means that our state sync is actually part of our start view protocol. So we request start view from primary replica, we receive start view, and then we get consistent checkpoint and log suffix from a primary, and we need to install it locally. And this is very important and something we've struggled with in the past quite a bit, in that you really want your log suffix and your checkpoint to be consistent. Because if you don't make sure that they are consistent, well, they could be inconsistent, and then you will get various injection failures when you try to validate the hash chain. Okay, so actually, let me see where we trigger state sync process. So like the initiation of a state sync is when a replica realizes, okay, I'm behind. And this is part of our repair procedure. So repair is just a function which periodically runs and tries to bring a replica up to date. And here we have this condition. So if we see that that our op, so the latest prepare we know about, is less than op repair max, which is more or less commit max, then we are going to send request start view to the primary, and then primary on request start view is going to create start to message and send it to us. So now then we, as a backup, we receive start view. And when we receive start view, like there is like three things which might need to change. So start view is a message which is sent from a primary, and it tells us the latest state of a cluster from the primary's perspective. But the primary always has the most up-to-date information, so the primary knows. Okay, and when a backup receives start view, it can advance three things. First of all, of course, it could just a second. I need to do something here. Okay, we are back. So when a backup receives starts view, it might need to adjust three different pieces of state. One is, of course, the view itself. If a backup is in view 5 and it receives start view for view 7, it realizes that, hey, like my view is outdated, so I need to switch to view 7. The second thing which the backup needs to do is that it needs to adjust its local log. So it receives start view receives a suffix of a log, and if this is the same view as the view that the backup is currently in, then it just appends those entries in the log. But if a view is different, it might be the case that the entries which the current node has are actually outdated, that those entries need to be removed from the log. So like when you insert your new headers, you might actually get rid of the headers you currently have, because they might be from the previous primary and they weren't actually committed. So to kind of give you some intuition like why you might need to actually replace your headers. So I mentioned that everything's normal. You're a backup and you receive a message from a primary, and the primary say, hey, the next operation is operation X. But it so happened that you were the only replica in the cluster who heard about this operation X. And immediately afterwards, the previous primary died. And the new primary got selected for a view change. Well, now that new primary might actually communicate it with the quorum of replicas, excluding you, and it might have committed some stuff. And then that primary also died, and the new primary got selected, and the new primary correctly picked up the committed message, which was Y and not the X you had. And then you hear from that third primary, and that third primary says to you, hey, actually, you know, you have like your X message and the slot, but actually it should be Y. And well, in this case, you like have to bump X from your log and it's set to Y, because this is like fundamental property of any consensus algorithm. You don't get to immediately know whether something is committed or not. You first learn about it, then you reply with prepare OK, saying that, hey, actually, I have this data locally on disk, so if it becomes committed, I can guarantee its durability. But you don't know if it is committed or not. It becomes committed only later when there is a quorum of prepare OKs. Okay, so covered so far two aspects of state: the view itself, then the log. And then finally, there is the checkpoint. Because if you are a login replica and then a primary replies to you with its log suffix, it could be the case that you, well, cannot append all the messages from this start view message to your log, because like your log is only one checkpoint long. So like there is like your checkpoint, and then there is like 1,000 messages you can append on top of this checkpoint. And any messages further in the future, they are actually not appendable to your log, because there is invariant that the difference between checkpoint and any message in the log is less than journal slot count. So if this is the situation, where you cannot actually append primary messages to your log, then you also need to update your checkpoint. And you sort of need to update checkpoint in logstep with your log messages. Okay, so let's see how it actually is implemented in the code. The key if here is this. So we receive start to message, and we need to decide whether we want to actually go and upgrade checkpoint. And you really want to avoid the situation where you have to install a new checkpoint, because it is much faster to get to a particular checkpoint by starting from the previous checkpoint and just replaying the prepare messages by just running the normal commit messages, because transferring the entire state is actually kind of painful. There is a lot of data there. So you only need to do that if you're really sure that it is a good idea to do this. And here we need to carefully think about when that makes sense. And this is related to a different function, op repair main. So okay, I guess here I will require some more diagramming. So we did a lot of diagramming last time, but I think it's not enough diagramming. We need more of it. Okay, let me. What is happening here? Why my drag and drop behaves so weirdly? Okay, this is like, I mean, even macOS is broken these days. This is ridiculous. Okay, could you? I mean, okay, let me try again then. Okay. Okay, this is better. Okay, so let's imagine that we have our log, and our log is finite. So there is the start of our log, the end of our log, and there is 124 entries here. And let's say that, like, you know, maybe this point over here, like at the start of the log, is our current checkpoint. And let's say that this place over here is our next checkpoint. Because, like, in general, like, you know, there isn't a very strict relationship between the length of our ring buffer for write-ahead log and the size of a checkpoint. Well, obviously, our ring buffer needs to cover at least one checkpoint, but actually it could be like, you know, it could be like quite a bit bigger. Like it could be like all the way here, so that we have like several checkpoints. And it would not work to make it exactly a checkpoint. It needs to be a little larger, but that would become clearer slightly further down the lane. So for now, let's imagine just this situation. So that's the start of like this current checkpoint, and that's like the next checkpoint. And let's say like we are like somewhere here, so we have all the prepares in this region, and we don't have prepares here. So here there is like nothing, and we haven't yet reached prepares over here. The question here is which prepares we have to have in our logs. Like obviously, like, you know, if someone asks us about the prepare which was like way before, so for example we are at prepare 10,000 and someone asks us about prepare like 5,000, we kind of like say, hey, no, we kind of like, we don't have it, and we don't even need to have it. So it's obvious that it's like, you know, very far in the past, but it's not entirely clear just how far in the past you need to go. So obviously, the first hypothesis here is that you only ever need the prepares between where you are currently at and the last checkpoint. But that's actually not correct. So imagine that we went all the way up here. So we have prepares for the entire checkpoint. And we have just achieved, got to the next checkpoint. So you might think that at this point, actually, we no longer need those prepares. Like we only need prepares like on top of our latest checkpoint. But that would be incorrect because you are not a single replica in a cluster. So you might be here, but it also could be the case that, like, you know, you actually are the replica which is furthest ahead of any other replica. So it might be the case that, like, you know, okay, let me do this. The picture might look roughly like this. So the log of this replica is kind of like, you know, it has gaps. And the log of this replica has gaps. So you see here, like for every place in the log, the corresponding prepare belongs to at least 2 replicas. This one and one of the replicas below. But the topmost replica is the only replica which has all the prepares. The replicas below, they actually have gaps. And so this replica actually, like, you know, it would be here because it doesn't have prepare over here, so it would be able to commit. And similarly, this replica here would actually be at the very start because it doesn't have the first prepare on top of the log. Now, in this picture, if at this point, the topmost replica says, okay, I no longer require any prepare which is behind the checkpoint. So I'm just going to evict them. Like, you know, just don't care about repairing them, maybe even like overwrite them. Then we get in a bad situation because we had a prepare which was replicated across two replicas, but now each prepare belongs only to a single replica. So if we now crash this prepare, like because there is like some error on the storage, then the data is irrevocably lost, because these two replicas, they cannot actually, like, proceed further because, well, prepare is lost. Well, you could say that, okay, maybe they cannot proceed with normal repair, but maybe they could actually reuse the checkpoint because, well, this replica has checkpoint. But remember, we kind of like want to make our cluster resilient to uncorrelated disk faults. So if this checkpoint actually gets corrupted on disk, then, well, this is a different fault from this one, because this one here is write-ahead log, this one is checkpoint, so those are completely unrelated triggers on disk, and they could get corrupted independently. So we don't have correlated faults here. For every place on disk, there is only one replica which has this place corrupted. Nonetheless, the cluster is stuck because it cannot use this checkpoint, because checkpoint is corrupted and checkpoint exists in only a single copy outside the cluster. And the same goes here. Like, this prepare exists only as a single copy, and it is corrupted, and now no one can fix it. So this is, again, this like physical logical distinction. To survive disk faults, the invariant we want to maintain is that at any given point in time, any specific fragment of data is duplicated across a quorum of replicas. If our cluster is cluster of 3 replicas, we want every single datum to be duplicated to at least 2 replicas. And in this picture, so before we got to our faults, we have a situation where each datum is replicated logically across a quorum of replicas. Because, like, the data in this prepare, it is here, and it obviously kind of like, the results of this data are in this checkpoint. So logically, this data is replicated. But physically, it is not actually the case that the data is replicated. Physically, this prepare and this checkpoint are different. And you cannot use checkpoint to repair the prepare, and you cannot use prepare to repair the checkpoint. Well, you kind of like, well, because, yeah, without this prepare, you actually can't get to the checkpoint. So that means that we need to be slightly more conservative. It could be the case that, like, we are past checkpoint, so we are somewhere here, but we still have to maintain some of prepares from the previous checkpoint. And specifically, the invariant here is that, let me collect my thoughts for a moment. The invariant here is that we can completely switch to a checkpoint, and we completely remove preceding prepares only when the checkpoint itself is replicated on a quorum of replicas. So if this replica gets to the checkpoint, then at that point we have 2 replicas at this checkpoint and could start erasing prepares from write-ahead log. So in this situation, this is actually fine. So this replica down here, it won't be able to repair using the log because prepares again, but it will be able to repair using state sync, because we have 2 copies of a checkpoint, and even if 1 copy of a checkpoint is corrupted, there is a second copy which could save us. Coming back to the code, this is exactly the interplay here between when we decide to sync to a checkpoint during start view and when we decide that we no longer need a particular prepare. And let's start with this operation op repair mean. So this op repair mean obviously okay, let's see where it is used. Yeah, so this op repair mean is used in our repair protocol, and we only repair ops which are higher than op repair mean. And this is how this op repair mean is defined. Normally, op repair mean is just our op checkpoint plus 1. So op checkpoint is the operation which is already checkpointed. So op checkpoint, like we don't need it. We already replayed its results. The earliest operation we need is like op checkpoint plus 1. But this only works if our checkpoint was already duplicated on a quorum of replicas. And this is what checkpoint durable does. I guess it doesn't make sense right now to understand why this gives what this gives. So why like op checkpoint durable, why its implementation needed enforces the invariant that, hey, if op checkpoint durable returns true, then the checkpoint is present on a quorum of replicas. But that is that indeed what this operation does. So if our checkpoint is replicated, then we repair from the checkpoint. Otherwise, we take the same number and step back by the exactly checkpoint. So VSR checkpoint ops is exactly like, how many ops are in a checkpoint. And it's, I think 124 is our overall log. And then checkpoint ops is like slightly less than that. But I actually don't remember exactly what this number is. Okay. And the same applies here. So we receive the checkpoint. If the checkpoint, okay, so this is going to be slightly tricky. Okay, so op checkpoint is our current checkpoint. Op checkpoint next is the next checkpoint. If we are going to state sync, then we are going to state sync either to the next checkpoint or to the checkpoint even beyond that. And we must make sure that at least the next checkpoint is durable. Because if it is not durable, if that checkpoint is not replicated on a quorum of replicas, then it is guaranteed that all the replicas maintain prepares from our current checkpoint. And that in turn guarantees that we will be able to sync up with the cluster using the normal repair protocol. So we don't have to state sync. Okay, and then the situation gets tricky. So now, if it so happens that not only our next checkpoint is durable, but a checkpoint after that is also durable, then we are hopelessly behind the cluster. And in particular, the prepares we have in our write-ahead log definitely are no longer contributed to the cluster's overall durability. So this is like hopelessly behind case where we definitely want to state sync. Otherwise, it is kind of interesting. So we know that the next checkpoint is durable, and we want to sync to it. But the question, like, should we sync to it or should we try to repair? And the answer here is that it might be the case that we don't have to sync. It might be the case that we will be able to proceed by using just usual repair, but also it might be the case that we are required to state sync. And the idea here is this. The idea here is that we try to avoid state sync and try to do a normal repair. And if it fails after some time, only then we go and do switch to state sync. So this is what repair stack does. So repair stack means that we are not able to proceed with our normal repair, which means that we are likely missing some repair, which means that likely the cluster is on the next checkpoint and just doesn't have its repair available anywhere. So let's see what are the important conditions here. So this one is like, I guess, most important one for understanding. Like, what does it mean that, like, we aren't able to repair our log? Well, it definitely means that we, like, still have something to repair, that we haven't caught up with the cluster. Commit max is the op which is committed by the cluster as a whole, and commit min is the op which we committed locally. Commit min is always less or equal to commit max, and if they are equal, we are up to date. Then it might be the case that we are checkpointing right now. So actually, we are not stuck at all. We are actually, like, going and updating our checkpoint, and we'll have like a new checkpoint like in the moment. Because again, everything is concurrent. You might be checkpointing due to normal operation processing, and at the same time you receive in start view, and you need to figure out what to do here. So it's normal. And again, here, like, if you're checkpointing, you're probably not stuck. Recovering head. Okay. So self status recovering head return false actually does look like it might be a bug, perhaps. Let me see. Okay, this is suspicious because if we are recovering head, it feels like we might have to state sync at the same time, and we don't necessarily want to wait for this case, perhaps. Well, or maybe not. Okay, no, I think it's fine, but it's okay. It's fine, but it's tricky, so I'm not ready to like actually explain recovering head. I guess we'll have a separate dedicated episode for looking at recovering head. Okay, actually, and I should start making notes for future episodes. Look at the recovering head state. Okay. So actually, yeah. Okay. Then we have like a little, like, progress tracker thingy. So anytime we actually make a progress, we set this advanced to true. So this is Okay, yeah. So every once in a while on a timeout, we see what was our commit mean before timeout, what is our commit mean now, and if they're different, then we like advanced. So okay. So we haven't made a progress for some time, and it is also the case that we either don't have the next header, or we don't have the next prepare, or we don't have a grid block which we need for compaction or commit. Okay. Now these are the two conditions where we want to, where we received a checkpoint from primary for the start, and we realize, okay, we do want to jump to this checkpoint. We do want to trigger the state sync. There is also this like self-syncing awaiting checkpoint, which I'll cover a little bit later. And actually, I am like started a pull request to remove that like a month ago, and I need to finish it. But it's kind of like technicality. Okay, so. Here, we realize that, hey, oh dear. I was thinking about like, it's actually like goes pretty fast, and we'll finish this thing surprisingly fast. And now I realize that I actually need to explain like this whole cancellation thing, because this is like very, very interesting. So okay, you receive the message and you realize that, okay, I need to sync. So what do we do next? And this is interesting. So okay, let's rewind. When we sync, well, we sync when we fail to progress normally. Well, and what does it mean that we fail to progress normally? Well, that means that we get stuck. And this could be like very, very brutal. So, we might actually get a prepare which we want to commit. So we are in the so we are like, in the commit dispatch loop, and we realize that, hey, we do want to commit, and so we go and we start with commit prefetch, and we call state machine prefetch. State machine prefetch, and that goes prefetching, I don't know, prefetch create transfers, which means that we need to prefetch the actual account. That calls into prefetch function to enqueue the account, and then it calls the prefetch. Well, no, it's not a prefetch finish. It is. Where does this? Well, it's not state machine prefetch. Okay, we are in a state machine. Prefetch finish. Oh, right. Okay. Yeah, right. So we first enqueue all the IDs for prefetching, and then we go to the groove and call prefetch. And this thing is going to start reading data from disk. So somewhere like in the workers, we are going to read. Okay, so probably it's going to be lookup from. Yeah, it's going to be like lookup from level storage inside the worker, and that thing is going to do a bunch of reads. So yeah, finally, like we do like a read block. So kind of there's like a lot of like complicated code, a lot of functions on the stack, and like this all bottoms out that hey, like we have written a block from disk. And now, like remember, we're thinking about the state sync. So this block is not on our storage because, for example, it got corrupted. So we go and we ask for this block from some other replica. But because everyone is way ahead of us in consensus, they actually no longer have this block in their storage. Like the block is gone. Like there's no way we could complete this commit operation because the data for computing this particular commit is no longer in the cluster. Like we know, the future state, like the future checkpoint, but we know but we don't have enough of state to reach to that future state using normal things. So we kind of like need to actually go and abort the in progress operation. And let's actually look at how that. Okay, so I guess maybe not. Let's maybe just make a mental note here that hey, we need to implement cancellation, and let's look at the cancellation in a week. And now just see how the rest of the state sync works. Okay. So we are on start U. We realize that hey, we need to state sync. So what we actually do here is that we request cancellation. And the thing about cancellation is that it's actually going to be asynchronous cancellation. So this is like, the thing that Rust struggles with. At this point, we have like some asynchronous work scheduled. And we cannot just blindly, say, okay, now we don't do this work. Because it could be the case that at this point in time, there is some write, like actual syscall for reading or writing data from storage, which is executed by the kernel. And we kind of like really want for that syscall to finish before we proceed with cancellation. So this thing is asynchronous. And this is like why this awaiting checkpoint state is needed. So because this thing is asynchronous, we actually need to finish, to wait for checkpoint to finish. And if we are like still canceling, then we actually just return. And after reconciliation finishes, it will flip our syncing state into await checkpoint. So we kind of like, this is the picture. We receive start view. We realize that, yeah, we do want to sync to the checkpoint from the start view. So we like cancel things. But canceling things also takes time. So we say, okay, I'm canceling things, but I really need that checkpoint, and I cannot append this checkpoint before I cancel things. So let me just ignore this start to message. And then at some point, cancellation finishes. And cancellation flips our state variable syncing back to awaiting checkpoint. So when we next receive a start view, we'll also drop into this if, and we'll hit this self-syncing case. But then we wouldn't have to initiate the cancellation, because by that time the stuff will remain cancelled. So we will fall through here, and we'll get to this point, and we will say that, hey, This is the checkpoint. So this view checkpoint is the checkpoint we extracted from our original message, start view. So we say that, hey, this is the checkpoint we want to sync. And we say this by storing this checkpoint as our field. So if you look at the sync dispatch, what it does is essentially, like, after some sanity checks, it sets our syncing state to this thing. So we have this syncing field in a replica, which points to sync stage, which like handles like this constellation flow. But what's interesting here, like, is at the end we have this like updated checkpoint. So once we get here, we know that, hey, the next time, once we get here, we know that, hey, there is no in progress committed work, and we are going to update the superblock soon, and we are going to use this particular checkpoint state to update our superblock. So let's go back to on start view and see that. Okay, yeah, so we have like our syncing as updated checkpoint. Now, we do our normal view change protocol where we look at the headers we received from the primary in the start view, and we append the headers in our journal as long as they can fit. Because again, our journal is like ring buffer, and actually the primary might be like, very far ahead. But there is a twist here. And the twist here is that we use our effective checkpoint. So our checkpoint on disk might still be our checkpoint from disk might still be from the previous previous checkpoint. But we have this updating checkpoint in memory. And so where we compute this op prepare max, this max op which we can correctly append to our log, we kind of like say, okay, if we are not syncing, that's like, it's normal prepare max, but if we are syncing, then we use the like checkpoint we are updating to. Okay, so this is like our normal like start to update, and then in the end, either through transition to normal from view change status, or like if we didn't update the view, then like we manually call this view durable update. And then in this view durable update, when we are going to update the superblock, and I feel like we also need to cover superblock update in some detail, because I don't think we actually covered this well enough. Well, anyway, when we are going to update our superblock, we are going to pass our new checkpoint alongside our freshly computed view headers. So this is kind of like confusing. So let me try to dig out of the speed of confusion and try to explain what we have done so far. Okay, so we want to jump ahead in our state. We want to advance our checkpoint. But we cannot advance only our checkpoint. And similarly, we cannot advance only our log. Like log and checkpoint together atomically, they are the state of a VSR. And whenever we need to update those two, we actually update them atomically. Both are parts of a superblock. So in the superblock, you have view headers, which stores like the suffix of your log, and you have the checkpoint state, which stores the checkpoint. So we want to update those two atomically, which means that like first you in memory first you prepare like the new state, the new checkpoint, and new view headers in memory, and then you atomically update both of them on disk. And that's basically it. So you receive start view, which contains the checkpoint, which contains the log suffix. You look at them both. You merge those with your existing checkpoint and your existing view headers, and you get the diff. You get a new checkpoint and the new headers, which you need to write to disk. And then you go and write them to disk. And the complication here, and which we'll look at next week, is that you might also be in the middle of a commit, because the reason why you are state syncing is highly likely is that you cannot complete your commit process. So before you actually can go and just completely replace your log, completely replace your checkpoint, you actually need to make sure that you don't have like any in progress operation hanging there. Like you need to cancel this. And that's what we're going to look at next week at 5 p.m. UTC, live on Twitch and on YouTube if you miss the Twitch. Okay, so yes, today's stream was like very hard. I feel like my brain is fried because this is like pretty hard code. So don't worry about this. The next time is going to be cancellation, which is even more fun. Hopefully you will enjoy it. And goodbye, and see you next week.